Hey folks, welcome to this lesson on reactivity and melting points, both periodic trends in our periodic trends series. What we're going to look at is the character of atoms and their electronegativities. Electronegativities in this case is symbolized by the symbol X here. So elements with high electronegativities, very, very negative electron affinities, and large ionization energies are generally non-metals. What this very negative electron affinity means is that they're going to give off a lot of energy when they gain electrons. The large ionization energies means that they're going to really put up a fight and they don't want to lose electrons. So things that don't want to lose electrons but just want to gain electrons, well, they're regarded as non-metals, and we've seen that through and through before. Elements with low electronegativities that have electron affinities that are low positive or very, very small negative values, and also have very small ionization energies are generally metals. What this low electron affinity means is that they don't want to gain, no gain electrons. Okay? The small ionization energy means that they want to readily lose electrons, okay? They're not going to put up a fight. They want to give that electron away. So things that don't want to gain electrons but want to, in fact, lose them are regarded as metals. And we can see here that our metallic character increases from right to left and from up to down. Now, what is metallic character? Well, think about what metals do. What do metals do? They lose electrons. Okay, so things that lose electrons are more kind of exhibiting the metallic characteristics. So do nonmetals lose electrons, these ones over here? No, they don't. They want to gain electrons. So we want to get as far away as possible, so we go to the left, and also we go down. Now, why is this one, these elements here, the most metallic character? Well, remember that these elements here are huge. They have massive amounts of shells. And in this case, if we look at that one kind of outer electron, it is shielded by all these inner electrons to get to that positive nucleus in the center. What that means is that there's less attraction and that this electron can be easily ripped off, aka easily lost. Lost as in what metals do, they lose electrons. So things that easily lose electrons are acting more like metals. On the other side, when we look at nonmetals, what do? They gain electrons. Okay, so they gain electrons. So things that gain electrons will be acting more like non-metals. So if we look at things over here, they have a high electron affinity and they also have a high ionization energy. They want to gain and they lose. They don't want to lose electrons. Things that gain and don't lose are acting like non-metals. So things that are higher up in the group and off to across the periodic table are going to be exhibiting more characteristics of non-metals. In terms of reactivity, the explanation is exactly the same. Metals react by losing the electrons, and the easier they lose electrons, the more reactive they are. Okay? So the easier something loses an electron, the more reactive they are. So remember, just from the slide before, these elements at the bottom are huge. Okay? They're huge. So they have beaucoup, a lot, of shielding. Okay? This reduces the attraction between the nucleus and the electron, and it loses an electron easily. Okay? That is an increase in metal reactivity. Metals here will still lose their electrons, but not as easily as metals at the bottom. If you go back and remember our little explanation of lithium, sodium, potassium, as we went down this group from Li to Na to K, okay, you can see that the ability for these elements as we go down to lose their electrons, it gets easier. The easier they lose their electron, the more reactive they are. And that's what we saw with lithium, sodium, and potassium. When we put lithium, it kind of fizzed around. When we put potassium, it exploded almost immediately. On the other side, when we look at fluorine, okay, as you go up this way, you have more of a chance of gaining electrons. Okay, that's what they want to do, gaining electrons here. That reactivity, the reactivity of the nonmetals, is all based on the ability to gain electrons. So here they have, again, a high ionization energy and a high electron affinity. They really, really, really want to gain those electrons, and they really, really, really don't want to lose those electrons. So they're going to be fighting to get the electrons. The more they fight to get the electrons, the more reactive they're going to be. So here's a general trend of reactivity, and we're going to move. Melting point. Okay, so melting point. Melting point is different for metals and nonmetals. When we look at metals in general, as you go down a group, the melting point generally decreases, and this has to deal with the way they bond. It's something called metallic bonding, and the model for it is called a sea of electrons. Okay, now we're going to go through this a little bit later, but just know that as you go down, you're going to have a lower melting point, and it's all due to this kind of model of bonding. With the nonmetals on the other side, as you go up a group, the melting point usually decreases. So what happens is that as you go down this group, okay, the melting point, you'll have an increase in melting point. Now, what you have to remember about these nonmetals is that they usually bond to one another. Okay, so in this case, we have fluorine and fluorine, and in the middle, we have a very nice, strong covalent bond. However, this is not the bond that dictates the melting point. If we have another a molecule of fluorine, there's an interaction between these two molecules, and this interaction is called an intermolecular force. Now, there's different types of intermolecular forces, but the main thing is that they are weaker than covalent bonds. Now, what happens is that as you go down a group, you're going to have more electrons. More electrons means more intermolecular forces, so it's going to be slightly bigger as you go down. And that's the main point for nonmetals. There is an anomaly on this periodic table, and that's in carbon. Unlike these nonmetals that form these intermolecular forces between themselves, carbon doesn't form any of these weak intermolecular forces. It's all bonded together using very, very strong covalent bonds. And because of that, you're going to have a very, very, very high melting point in this case. So once again, there's your general trend. So here's a summary of many of the trends that we looked at. We looked at atomic radius. Okay, it's bigger over here because you have more shells. And also as you go to the left, you're going to have less nuclear charge, which doesn't pull the electrons in as tight. Ionization energy and electron affinity both go this way, as well as electronegativity. It's the same direction, and that's again as you go from left to right, you're increasing your nuclear charge, the amount of protons in the nucleus, which pulls the electrons in tighter. In terms of ionization energy, it requires more energy to remove. In terms of electron affinity, it will accept and release more energy, and electronegativity is going to pull those bonding pair of electrons toward themselves. As we go this way, okay, you're having less and less shells, which means that you're going to be closer to the nucleus. More of an attraction is going to pull everything in. Okay? And that's it for the trends, guys. Thanks very much. See you soon.